Hi students. So today we will discuss kinetic theory of gases part 3. Already I uploaded part 1 and part 2. So please go through it part 1 and part 2, then come back to the part 3. So in this chapter we will study mean free path and specific heats, molar specific heats, and method of mixtures now, right? Mixing of our gases now. So first let us go for mean free path now, right? So mean free path. So what is the meaning of this mean free path, right? See, anytime if you don't know any formula or any statement, no, please try to observe the statement, then you will get it as mostly the information related to that. In this one, no, mean free path. So mean means what? Is nothing but a average. So it is nothing but a free, therefore the molecules has to move freely. So path means total distance. That means, so freely means what? Before colliding from one particle to another particle, how much amount of average distance to be traveled by the molecule, we'll call it as like a, so mean free path. Mean means average, so mean free path. Understood, no? So average distance to be traveled by the molecule, so before going any successive collisions, no. So therefore here there is a one gas is there, no. So this is one gas is there, no, inside this one, no. So these are the molecules are there. Molecules are very very far away. So therefore it will go some distance, like let us assume that lambda 1. So then it will go some distance like a, so lambda 2 to go for another collision, no. So it will go from lambda 3. So like that it will go some other distance, no, lambda 4. So what will be the mean free path now? Mean free path means nothing but a average distance. That is nothing but a lambda 1 plus lambda 2 plus lambda 3 plus so on up to lambda n divided by n. So this is an average distance to be traveled by the molecule, so to undergo like a successive collisions now. So this mean free path from the kinetic theory of gases already derived one equation, no. What is this equation? So listen carefully. Mean free path. Mean free path means distance. So what is a unit, no? Unit is nothing but a meter, right? So therefore mean free path is given as a formula 1 by square root of 2 into pi into n into d square. So this is your mean free path formula now. What is this formula now? So lambda is equals to 1 by square root of 2 into pi n into d square. So n is what? N, d is nothing but a diameter of the molecule. Diameter of molecule. So what is n? N is nothing but a, so number of molecules per unit volume. Therefore number of molecules per unit volume. This is the value of n onto this. Clear, right? N is nothing but a, so number of molecules per unit volume. Therefore, so mean free path is inversely proportional to the square of the diameter. That means what? So if a bigger molecule is there, bigger size, no. So therefore bigger molecules, it has to travel less distance to collide, because very big fat persons are there. He will be colliding very frequently to the other particles now. Suppose one small lighter particles are there. Lighter means small path is there. So it has to travel longer distance to get collided onto this. That is the relation here now. So therefore lambda, that is inversely proportional to the, it is molecular density. Molecular density, that means if more molecules are crowded means more number of molecules are there per unit volume. That means all molecules are crowded. So therefore crowded people, no, compulsory will have a collisions very very frequently. So therefore there at that time less distance it has to travel. So if molecular density is very far, very high, that means so very big volume, it is occupying less number of molecules. So it has to travel longer distance to get collided onto this one. Clear? So in this way we can calculate it, no. So we'll just modify some more formulas related to this one, no. Let us see. Here mean free path, what is the formula? 1 by root of 2 into pi into n into d square. Mostly the formulas, this formula itself they are asking in the examination, no. So we'll see. So n is what? Therefore number of molecules per unit volume. So what you can write it now? PV is equals to NKT. Can I write it now? So here, so therefore P by kT, it will be equal to n by V. Therefore, I am taking here no. So this all I am taking down. Clear? So n by V, this is nothing but a small n. So what you can write it now? So mean free path, it will be equal to 1 by square root of 2 into pi. N value is nothing but a, so therefore here P, therefore KT into therefore D square. Free path can be calculated as KT by this one now. But you can see here now, therefore P by T, number of these molecules per unit, number of molecules per unit volume, this is constant now. So therefore, so P by T or T by P, therefore T by P, so this is always constant. So if temperature changes, pressure is also changes onto this one no. So therefore mean free path is does not depend on P and T now. Clear? So therefore again, so mean free path we can rewrite it as, so one more formula, that is nothing but if I multiply with mass m, mass of each molecule, mass of this one now, therefore mass of each molecule into n means number of molecule, that means total mass of this one now by volume into mass of this one now. Mass per unit volume is nothing but density by mass of this one. Clear? So here we can rewrite it as mean free path, it will be equal to 1 by square root of 2 into pi, n value is nothing but density into mass into D square. Clear? So in this also you can write it now. But sometimes they will ask you what is the collision time or collision frequency. So if they are asking now what will be the average time no, therefore, so if you know the speed of the particle no, therefore mean free path by time, so therefore this is the time, therefore mean free path by velocity of the particle, this is the time taken to get successive collisions onto this. Or sometimes they will ask you collision frequency. So what is the collision frequency? So collision frequency is nothing but so 1 by time, therefore reverse of this no, that is nothing but V by lambda. Like this questions also you can expect it now. So we'll do some numericals onto this now in the separate part of this. So meanwhile you try to remember this formulas onto this formula. In this formula is very important. Now okay, so now we will go for another one more concept no, that is molar specific heats now. Molar specific heat capacity. Molar specific heat capacity. Right, what is meant by molar specific heat capacity? We already studied in heat lesson what is meant by the specific heat now. What is the specific heat formula? We already studied no. So therefore Q is equals to ms delta T. So therefore S is nothing but Q by m into delta T. So what is this now? A unit mass of the substance 1 kg per 1 degree raise in temperature. So specific heat is nothing but amount of heat energy required for unit mass of the substance to raise 1 degree raise in temperature, that is said to be like a specific heat of the solids and liquids we studied now. But in terms of gases now, when you are supplying the heat energy for the gases, you have to take the conditions like this. See, therefore either you have to keep the volume at constant now, or you have to keep the pressure at constant onto this. That's why, so molar specific heat capacities, so we'll be having two values onto this now. One is at constant pressure and constant volume. So we'll get it as like a constant volume, and also molar. Here it will be mass is there. Here for gases no, therefore moles we will calculate it now. Constant volume, therefore we'll write it as at constant volume. So that means we are heating the gas at by keeping the constant volume. So therefore amount of heat energy supplied for unit for constant value, here number of moles, here mass is there, here number of moles, N is the number of moles into CV into delta T. So what you can write now, CV is molar specific heat right at constant volume now. Therefore what you can write now, delta Q at constant volume into N into delta T. So what is the SI unit for this one now? This is SI unit is nothing but a joule per mole, therefore Kelvin now. What is the dimensional formula here now? Dimensional formula, therefore M1 L2 T minus 2, so K minus 1 mole minus 1. Right, this is the dimensional formula for molar specific heat at a constant volume. Similarly, at constant pressure also we can write it now. Same way, therefore, at constant pressure. What is this constant pressure now at constant pressure? So here, therefore, you can write it as amount of heat energy per unit constant pressure. Therefore, N into Cp into delta T. Cp is nothing but a delta Q at constant pressure by N into delta T. Clear? So that means what is this Cp and Cv now? Therefore, here for 1 mole of the substance to raise 1 degree raise in temperature, let us see. For 1 mole of the substance, 1 mole of the substance to raise 1 degree raise in temperature, no? Therefore, amount of heat energy required for 1 mole of the substance to raise 1 degree raise in temperature for a given mass of a gas at constant volume is nothing but a molar specific heat at a constant volume. Like that, at constant pressure is nothing but a Cp. Clear? So we can have some relations between these two. So that is Cp and Cv. So therefore this derivation, no, so we have to use first law of thermodynamics to derive this one, no, but I am not going for this. So Cp, therefore we can write it as like a Mayer's relation. What is this Mayer's relation now? Mayer's relation. So therefore Cp minus Cv is equals to R. So for this gas, this equation, no, it can be applicable for monoatomic, diatomic, triatomic, all the polyatomic gases, no, this formula is applicable. Now we will write down. So we know, so gamma is nothing but what a ratio of the specific heats, no, that's for Cp by Cv. What is the formula here now? Gamma value we can write down 1 plus 2 by F. So what is 1 plus 2 by F now? F is nothing but a degrees of freedom. Degrees of freedom. So what are degrees of freedoms? No, therefore I already discussed in part 2 of our kinetic theory of gases. Please check out this one now, degrees of freedom. So just remember that for monoatomic gas, no, for monoatomic gas 3 degrees of freedom. For diatomic gas, therefore 5 degrees of freedom will be there, 3 translational, 2 rotational now, right? Minimum thing you can remember, no? Therefore here, then, so we want to write down this Cp and Cv in terms of gamma. How to write it now? Listen carefully. So here Cp is equals to gamma into Cv, gamma into Cv. So Cv taken common now. Therefore, so you can write down R by gamma minus 1. So similarly Cp, so you can write down Cp is nothing but a, so gamma into Cv, therefore gamma into R by gamma minus 1. These are the Cp and Cv in terms of gamma now. Very simple mathematical, no? So we'll write down gamma value for monoatomic. So for monoatomic, what is the gamma value now? Gamma value for mono, so you can write down 1 plus 2 by 3, that is nothing but a 5 by 3. So gamma value for diatomic is how much now? 1 plus 2 by 5, so therefore 7 by 5. Substitute it now, therefore Cv. So Cv value for monoatomic. What is the monoatomic value here now? Monoatomic. So you can rewrite it as R by, therefore gamma minus 1. So for mono 5 by 3. 5 by 3 minus 1 means is 2 by 3. Therefore 3 R by 2 will be your Cv value. Similarly diatomic value, diatomic gases for Cv value, how much now? R by, therefore 7 by 5. So therefore it is 5 R by 2. Right? So this it will be the Cv value for diatomic. Similarly, Cp value, so for monoatomic, what you will get it now? Cp value. So therefore here gamma multiplied onto this 5 by 3. So 5 by 3, so into Cv value, therefore what will get now? 3 cancel, no? So 5 R by 2. So similarly Cp value for diatomic, no? Therefore here it will be 7 by 5. Therefore 7 R by 2. So these are the Cp and Cv values for mono and diatomic gases. Clear? Right? So similarly one more formula we can rewrite it as, no, if we are calculating amount of heat energy for diatomic like that, no, therefore amount of heat energy at constant volume means NCV into delta T. So for mono or dia means you have to substitute the Cv value, right? So for monoatomic, diatomic, that values, you have to substitute it now. Similarly delta Q, amount of heat energy supplied for the gas at constant pressure, therefore NCP into delta T. Therefore, if it is monoatomic gas, Cp value you have to substitute. If it is diatomic gas, no, you have to find the Cp value and you have to substitute and you have to calculate it now, right? So, we will do some more questions on this one now, numerical questions related to this one now. Clear? Now, so these are about the specific heats now. Next, we already discussed the mean free path now. Right, we will discuss one more topic now, that is method of mixtures now. Right, so here method of mixture of gases now. Here we are going to take the two gases, two or more gases now. So, but they are said to be like a non-reactive. That means there should not be any chemical reaction should not be takes place now. So, let us see here. So, there is a one gas is there no. Therefore, here one gas is there. So, this gas is kept in the one container. Therefore, it is having the pressure P1. So, having the volume V1 at some temperature T1. So, another one more container now. Therefore, it is having, so some more gas is there now. Therefore, here at pressure P2, therefore at volume V2 at temperature T2. Therefore, these two are combined in one more container now. So, therefore, which are non-reactive, which is having final pressure is P3, final volume is V3, so final temperature is like a T3. So, therefore, if these gases are mixed like this, no, so what we have to do? See, simple thing, law of conservation of mass cannot be created, not destroyed, no. So, how many number of moles of the gas is there, no? Plus of this one, no? That many number of moles of the gas it will be present onto this one, no? So, always remember that in method of mixtures, no? So, number of moles, so it should be equal to N1 plus N2 plus N3 plus so on up to Nn. You understand, no? So, here only two are there, no? Two gases are there, no? So, N is equals to N1 plus N2. How to write it now? Simple thing. Therefore, here, so total combination of this one, no? You know that PV is equals to, therefore, nRT. So, N is equals to PV by RT. Therefore, substitute here, no? So, therefore, P3, so V3, R for this R, for this R, for this R, it will be universally constant, no? T3 is equals to P1 V1 by T1 plus P2 V2 by T2. Like this, you can calculate it, no? So, about the mixture of the gases, right? Sometimes, if these two are combined, so with some small pipe, no, then what you will get it now? V3 is nothing but a V1 plus V2. Clear? Like that. So, V3 what will be the final volume? Also you need to calculate. Right. So, we can see some condition here, no. So, suppose there is, okay, this is a final pressure, no, we can rewrite it as, if the volume and temperature both are same, no, therefore, P equal to P1 plus P2 plus P3, so on. So, this is only nothing but a Dalton's law operation, no. So, what does it mean now? This is one gas which is at one constant volume, one fixed volume at particular temperature. This second gas is also kept at same volume at same temperature. So, this is our third gas. Third gas is also kept at same volume at same temperature. If you mix all these three at same volume at same temperature, it will be equal to the sum of all the pressures. This only we will call it as like a Dalton's law of pressure. Clear? Right. Like this, Dalton's law of pressure was given, no. So, if suppose they are mixing with a some mass onto this one, no, therefore, we can calculate that is like a molecular weight of the combined gas. So, what is the molecular weight now? Molecular weight of the combined gas, no. So, combined gas, what you can write it now? Number of moles of the combined gas. So, therefore, N1 plus N2. So, two gases are there into molecular weight of the combined gas will be equal to, so N1 into molecular weight of the first gas plus N2 into molecular weight of second gas now. Therefore, so molecular weight of the mixture, you can write down N1 M1 plus N2 M2 by N1 plus N2. In this way, so we can calculate the molecular weight of a mixture of the gases. This is not important, no, but most important is gamma values, right? So, Cp of the mixture or Cv of the mixture. So, exactly the same way. So, what you can write it now? So, N1 Cv1 plus N2 Cv2 by N1 plus N2. This is molar specific heat at constant volume of the mixture of this one. So here Cp of the mixture, so you can write down N1 Cp1 plus N2 Cp2 by N1 plus N2. So what is the gamma of the mixture now? Gamma of the mixture, you can write down Cp, so mixture by Cv of the mixture now. So what you can write it now? Therefore here, so N1 Cp1 plus N2 Cp2 by N1 Cv1 plus N2 Cv2. Clear? So in this way we can calculate the gamma of the mixture onto this one. Clear? So we can do most of the times the questions are coming based on this only. So about the gamma of the mixtures onto this. Clear? So we can do one question now, simple question now. So therefore here what you can write it now, one question now. Suppose here 1 mole of monoatomic gas is mixed with so 1 mole of diatomic gas, right? So we want to calculate what will be the gamma of the mixture. So first of all you have to calculate Cp and Cv. So we already calculated Cp and Cv for monoatomic, no? So Cp for monoatomic and Cv for diatomic, right? What we calculated now? We already calculated. So right here. So for monoatomic 3R by 2, diatomic 5R by 2. So 5R by 2, 7R by 2, right? So these values only we will take it now. Right. Cp value for monoatomic, for mono. So what you can write it now? Therefore for monoatomic 5R by 2. So for diatomic, no? Diatomic, therefore 7R by 2. So Cv value, therefore 3R by 2 for monoatomic. For diatomic, no? Cv, so therefore here it will be 5R by 2. So we can rewrite it as therefore gamma of the mixture, no? So here you can write down for 1 mole of Cp1 means how much now? For monoatomic, therefore 5R by 2 plus so 1 mole into therefore again this is 1 mole for diatomic, no? For diatomic, so Cp1, no? Therefore 7R by 2 by 1 into therefore Cv, so therefore 3R by 2 plus 1 into therefore 5R by 2. So here R by 2 taken common, cancel it now. Therefore you can write down 5 plus 7 divided by 3 plus 5. So therefore it is 12. Therefore it is 12 by therefore 8. So 4 3s are 4 2s are, so it will be 1.5. So will be the gamma of the mixture onto this, right? So like this you have to calculate right, so many questions on this one, no? So we'll do one more fully numerical based one now on full kinetic theory of gases, no? So these are the theory parts, part 1, part 2 and part 3. So go through it. So then we will do one fully numerical part on this kinetic theory of gases now. Thank you for watching my video. So please subscribe to my channel.